All right, so we'll get started here in a moment. Just working on my notes. Yeah, please make sure to sign in. All right. So let's see. So we've been talking about these new mathematical objects we call vectors. And there are two main things that every vector has. What are they? The two things that every vector has.
A right angle.
No.
Magnitude and direction.
Yeah. So a magnitude and a direction. These are the two things that define what a vector is. Now you can talk about the magnitude and direction, in different forms, but the main idea is that you have these two qualities. And if we have a vector, we'll call it R, magnitude, I just write as the letter, and the direction is theta. All right. So this is where we kind of started. But we also talked about the component form. Where R is equal to, we'll get this funky looking bracket. R with a little x means the x component. R with a little y, it's the y component. So the idea is, quite simply, you have a vector, and it can, you can talk about its magnitude and its direction outright, or you can talk about it in component form. And realistically, if I give you either two of these things, or any two of these four things, r, theta, rx, and ry, you should be able to find the other two. So last time we kind of left off, and I was trying to get you guys to tell me what are the relationships that relate all of these things. So that's where we will start back in. What relationships allow you to find, or go between Rx, Ry, theta, and R?
Law of cosine?
Law of cosines is close, but is actually more involved and too intricate. So remember, R is a vector. It has some length, which is R, and some angle, theta. If we talk about it in component form, it's like this. This is the x component. It's how far out in the x direction the vector goes. And then this is the y component, how far out in the y direction the vector goes. So what is the relationship between all of these? Like I said, you're kind of close on law of cosines, but it's way simpler than that. What is the shape that I've drawn up here?
Right triangle.
The right triangle. What just so happens to be true for right triangles?
The Pythagorean theorem.
The Pythagorean theorem. So one of the relationships that relates these things is r squared equals rx squared plus ry squared. So what about other ones? What one do we not have a relationship for?
Would it be sine, angle, side?
Again, I think you're thinking about it too hard. What of the four things, 1, 2, 3, and 4, do we not have a relationship for yet?
Theta.
Theta. So what is the relationship for theta?
Theta equals, however, I'm not for sure.
Okay, it's a right triangle. So what happens with right triangles?
180 degrees is what it equals.
So this is not good. So it's a right triangle. So there's a relationship between the cosine of this angle is Rx over R, and the sine of this angle is Ry over R, right? Anybody remember that from
Yes, sir.
ever? So these are the relationships that relate these four things. So you should be able, if given any two, so you could get these two and you can find these two. You could get these two and find these two. Or you could get Ry and R and you should be able to find the other two, and vice versa. So the idea is that you should be able to go between all of them at any time for any reason. Like that's just how this works. Okay. So let's take a step back here, and we're going to find all of these things. So first, we're going to start with 2 points. All right. So P 4, -7, Q -1, 5. So we're going to find the vector PQ. All right. What is the component form of this vector? What is the x component?
4.
No, it's not 4.
Is it P?
No. So remember, what does the x component mean?
The change of X?
It's how far the vector goes in the x direction. So what is the change in x, or how far does the vector go in the x direction?
3.
No.
Is it 3?
Nope. Where are you starting?
P?
You're starting at P. So what is the x component of P?
4.
Okay. Where are you ending up?
-1.
At -1. So what do you have to do to go from 4 to -1?
Subtract.
Subtract 5. What about for y? What is the y component?
+9.
So we're going from -7 to +5, which is what?
Positive 9.
If you add 9 to negative 7, what do you get?
Sorry, I got positive 12. I'm sorry.
12. I think I like that a little bit better. Okay. So, got there. This is the x and y component of this vector. So, what is the magnitude of this vector? Or how would we go about finding it?
The magnitude is 13, and I got that by doing the r squared equals rx squared plus ry squared formula.
So the magnitude, and the way we write it generally looks like this. Yeah, so it's the square root of 5 squared plus 12 squared. 5 squared is what?
25.
And 12 squared is,
144.
and what's 12 or 25 plus 144?
169.
And I agree. That is 13. Very good. All right, now we're moving. Now we're moving. So, last little piece of the puzzle. What is the direction? What is the angle of this vector? How do we go about finding it? Well, what's one of those relationships that has theta in it?
R times sine theta.
I'm sorry?
R times sine theta.
Okay, so we have r sine theta equals what?
Ry.
Okay. So what values go where in these? In this equation?
R equals 13 and ry equals 12.
So we have 13, 12. So that means that theta is the inverse sine of 12 over 13. Which gives us what? So I get about 67 degrees. Is that right?
Yes. So you don't have to put like the 0.38, just leave it as like
So, well, that's a fair point. I mean, you can have 0.38. Depends on, how far you're rounding it. But let's check to see if that is correct. So the other relationship is 13 times cosine theta equals 5. Well, cosine of 67, equals negative 5. $67.38 times 13. What do you get when you do cosine of 67.8 times 13? Anybody?
I got 112.62.
112? So what do you get in this when you do this? You should not get a number bigger than 13.
I apologize. I thought you were talking about the degree.
Oh, so you were solving for theta.
Yes, sir.
Yeah, that's fine. Well, what did you get? Okay, we'll go at it that way. That's fine. Cosine theta equals negative 5. What did you say theta equals?
Theta equals arc cosine negative 5 divided by 13, and I got it equals 112.62.
Equals 112.62. Well, that's not good because that means that our two angles are different. So what happened? Does anyone maybe notice anything interesting about that number?
Both of them add up to 180 degrees.
They add together to be 180. So this is part of the thing that you have to watch for, is you have to think about what the vector means. And sine and cosine are only adequately defined in certain ranges. So which way does this vector point? I guess we'll start with that. You have your axis right there. Which way does your vector point?
Towards the second quadrant.
Toward the second quadrant. Very, very good mathematical language. I like it. So, yeah, I mean, you could have said up and to the left, but much more accurate answer. It's going this way. So this is something that you need to think about when you are defining this kind of stuff. You need to think about where it points. Sine is usually will give you the correct answer if you do it in this area, in the first or fourth quadrant. And cosine will give you the correct answer when you do it in this area. Over here, both of them will give you the kind of a weird wrong answer. So you just have to think about, well, what answer is it trying, does it think that it's giving you? So the correct answer is 112, but 67, what is 67 on this graph? So what did we say was very interesting about the two numbers up here?
180 degrees.
They add to 180. So 112. So the number that sine gave you was actually this one. I guess I should have done it. Remember. So this is what you have to keep in mind, is what does the equation that you're putting in actually try to give you? Because it won't always just give you the answer. So you have to think about what quadrant are you looking at? What quadrant tells you which one you need to look for, okay? So you can do, if you're up here, you should probably do sine. I'm sorry, if you're up here, you should do cosine. If you're over here, you should do sine. Otherwise, it's going to give you a funky looking number. So it's just one of these things that you have to think about and stay comfortable with. Otherwise, if you just plug it in and go, it's likely you'll get the wrong answer. Because you always have to think about, what does it think it is trying to tell you? Okay. So this is how we find all of the different parts of a vector. All right. So that's within one vector. Now let's look at two vectors. The first thing that you can do with two vectors is compare them. Are they the same? Are they different? So let's look at how to compare two vectors. Oh, sorry, I'm working on my notes. Oh. So let's see. Let's draw a couple vectors. Are these two vectors the same?
Yes, sir.
Yes. Okay. So these two are the same. I agree. They look just like carbon copies of each other. That's fabulous and great. Okay. How about these two?
Yes.
Yes?
No.
Why do you think no?
Because the direction is different.
Because the direction is different. So they are the same size, they have the same magnitude, but the direction is different. And this is very important, understanding how we're actually comparing things in math all the time. Is the way you decide if two things are equal or not is if they have the same value, but they could have different measures of value. So people, for instance, you can't really define people by a single number. You could have their height. You could have their, their IQ. You have, this is especially common at like the NFL combine, whenever you're doing, looking for athletes. It's not just a single number. You care about their 40 time, their vertical leap, their horizontal leap. I mean, their bench press, like all of these different numbers. So in order for two things to be the same, then they need to be the same in all of those respects. So in order for two vectors to be the same, they have to have the same magnitude and the same direction, both at the same time. So they have to be the same size and pointed in the same direction. Okay. So this is comparing two vectors. Pretty straightforward. Do they have the same magnitude and direction? Well, comparing them is, like I said, pretty simple. But like every other mathematical object, once you've figured out how to compare them, what is the next thing that we pretty much always figure out what to do or how to do with vectors? Once you figure out, let's say with numbers, once you figure out how to compare different numbers, which one's bigger, smaller, that kind of thing, are two numbers the same, what's the next thing that you learn how to do?
Add and subtract them.
Add them and subtract them, exactly. So, okay. So, adding vectors. Let's start with our two vectors. It's kind of funny to think about. I know that, but just go with me. So these are my two vectors. How do I add them?
At the endpoints.
Add the endpoints? What do you mean?
I'm not for sure.
No, I like that comment. It's very good and very close. So I am just curious to see if we can get a little further. So add the endpoints.
Right.
What do you mean by that?
I was just thinking add the two endpoints until they make some sort of angle.
So like Guess I'll redraw it. So like that.
The opposite way, the opposite endpoints, like.
Okay, so add the starting points.
Right.
Okay. Like that.
Yeah, that's what I was thinking.
Okay. So you're getting close. Imagine the vector is some distance travel. So if you're going somewhere, you're going on a trip, your trip is made up of a bunch of little vectors added together. You go some amount north, you go some amount east, whatever. So, and then you end up at your destination. Well, how do you do your trip? Can you do both of these things at the same time? Can you go north and go east? So you have to complete one of the vectors before you can do the other one. So when you add them, and this is why I like your intuition. It's very close. But when we add them graphically, you put their endpoints, or you start the second vector at the end of the first one. So if we call this vector A and this B, this is A plus B. And interestingly, so if you add $1 to $1, do you get a fish? Or do you get 2 fish? What do you get?
$2.
You get something that is in dollars. So when you add 2 vectors, you actually get a new vector. Which is called the resultant. We're about to get kicked off, but this is how you add vectors visually, is this tail to tip method. And we will keep